Okay, this is a video to cover what I call the Fluorine-Francium Rule that I did in class for my students, and it goes through some demonstrations that I did as well. First of all, we've done our periodic table trends where we had arrows where we went down a group. Atomic radius got larger, going across the period. Atomic radius got smaller, and of course going up this side, it got smaller. And we noticed that all the energies decreased going down a group, but increased going across the group, and of course increased going up a group. There's a direct connection between these arrows and the reactivity of metals and nonmetals. And of course they are opposites of each other. Okay, well first of all, our nonmetals again are on this side of the periodic table, and our metals are basically everything else. They are opposites. So that's why I call this the Fluorine-Francium Rule. Nonmetals want to receive electrons and attract them over. Therefore, they want high ionization energies and they want to be small. So the atom closest to fluorine on the periodic table will have the smallest atomic radius and all the highest energies. And because that's what nonmetals want, then I call that the fluorine rule. The atom closest to fluorine on the periodic table, that is a nonmetal, will be the greatest reactive nonmetal. And why is that? Because the atomic radius is small and the energies are high. Now, of course, we are excluding this last group here because this last group are the noble gases and they're not very reactive at all. Now, opposite this, metals want to be large and they want their energies to be low. Why? Because they're trying to get rid of electrons. And that's where the Francium rule comes from. The element closest to francium will be the largest element. It'll have the lowest energies. And this is where the metals want to be. So the metal closest to francium, location-wise on the periodic table, will be the fastest reactor. Now, are there exceptions to these rules? Yes, these are just general trends, okay, that we've been investigating. Let's look at some demonstrations that I did in class. I demonstrated lithium in water, sodium in water, and potassium in water. And the atomic radius gets larger as we go down this group. Lithium is smaller than sodium, and sodium is smaller than potassium. Let's take a look at pictures of what this looks like. So let's look at the smallest atom, lithium. This is lithium's reaction in water. It buzzes around, okay, produces some gas, hydrogen gas, but you don't really see a whole lot of that reaction there. It's not really doing a whole lot. Now let's look at sodium. Sodium can actually catch on fire on the water, showing that it is definitely a faster reactor. But remember, that atom is a larger atom and closer to francium on the periodic table. Therefore, it does react faster. And now let's go one more down to potassium. Potassium kind of explodes in contact with water, makes these sparks, a nice purple flame, and reacts really, really quickly. Potassium is our fastest reactor in this series that I'm showing you because it's the largest atom and indeed is closest to francium on the periodic table. Let's go back, okay, to our periodic table and confirm that again. So lithium didn't react very much, sodium faster, potassium the greatest in the reactions. Okay, so as I go towards the right, we're going to notice that the reactivity of the metals actually goes down because we want to be closer to francium. So even this row over here, beryllium, magnesium, they're going to be slower reactors than their counterparts over here. So we expect beryllium to be slower in reaction than lithium and vice versa. Now again, remember, this is just general trends, and we're using the periodic table trends to predict the reactivity of things out there. You know, we may be correct, we may not be correct. It doesn't matter. There's an actual reactivity series based on electrochemistry where they'll give us our final correct answers. But we don't need to worry about that right now. And again, the nonmetals, I did not demonstrate in class because of their toxicity. You know, fluorine and chlorine are pretty toxic. You know, bromine, iodine can also be toxic too. So let's practice a couple of these. So let's say if I'm comparing silicon to phosphorus, and I want to know who is the faster reactor in this and make a prediction. Well, these are nonmetals, so I'm going to use the fluorine rule for them. So because phosphorus, right, is closer to fluorine, okay, on the periodic table, the phosphorus is going to be a faster reactor than the silicon. But that means phosphorus is smaller than silicon, and it also means it has higher ionization energy than silicon. Now again, that's just based on its predicted place in the periodic table. Going to be exceptions to these predictions? Yes. This lesson does not really cover any exceptions. It just says follow the general trends. Whoever is closest to fluorine will be the smaller atom and will have the higher ionization energy. Therefore, it will be the greater reactor for the nonmetal. Let's try this for metals. What if I'm comparing calcium to barium? Well, the greater reactor is going to be the one closer to francium. Well, barium is definitely closer to francium. So we expect barium then to be the greater reactor. Now, barium will also be the larger atom and have lower energy, like lower electronegativity, lower ionization energy, lower electron affinity. All the energy will be lower. So that's how we use the Fluorine-Francium rule on the periodic table to do general predictions based on the position of the element in the periodic table. We are not covering any stability rules or any exceptions that would be provided by looking at stability rules or looking at the actual reactivity series in electrochemistry. This is just very simple looking at general trends. And that's what I demonstrated in class.